So now we're ready to move on with what ends up being one of the biggest topics in this chapter, and that is what we get to, or what are called the integrated rate laws. The integrated rate laws are a series of equations that relate concentration of reactants to time. Our other forms of rate expression or rate law that we have so far, one has this form, okay, that we just worked with, and the other one that we started with has this form. This is our average, this is our instantaneous one over here, okay? This one on the left has time in it, but it's kind of got this average block of time, right? This one over here on the right is instant. How fast your reaction is at any given moment. You just don't know what moment it is. You don't know how much time you're talking about. There's no time factor in there at all. So what we need to do is combine these two. We need to get rid of the rate and solve these equations. To do so, we need calculus. And so we're not going to necessarily do the calculus here, but calculus has been used to solve this expression. So depending on what math class you're in right now, maybe you've started to do integration. All right? I think we do that in Calc 2 here. Calc 1 is mostly differentiation. Okay? So if you're in Calc 2 this semester, maybe you've started to do some integrals and solve them. And that's what you would need in order to solve this. If I could briefly show it to you, for one of these orders, what you would do is take this negative delta x over delta t equals k x to the n. So this would become, as delta t goes to 0, right? That's what calculus is. You'd make that delta get smaller and smaller and smaller, right? This expression over here becomes negative dx dt equals k x to the n. So you would want to solve this for negative dx x to the n equals k dt. So here's, or in other words, this is x to the negative n dx equals negative k dt. So if you're in a Calc 2 class, I encourage you to start to solve this now, all right, to do the integration. It's a great exercise. It links what you're learning in a different area of your curriculum to what we do in chemistry. Or is that blowing your mind, Morgan?
Yeah.
Why is that?
I don't know.
Are you in Calc 2 or not?
Yeah.
Okay, so have you started to do integrals like this?
Yeah.
Okay, so we are going to use the results of this for the 3 different values of n that we've been looking at so far in this chapter. We could do it for any value of n. Okay, what we do? We'd slap some integrals on here, and that's what we get. All right. So depending on what n is, when n is 0, the solution of this is that x, the concentration at time t, because I'm going to integrate my time from 0 to t, whatever time I'm interested in, just generic placeholder. So the concentration at time t would equal the concentration at 0 minus k times the time t. Okay? When n is equal to 1, the form is going to be the ln of the concentration at time t equals the ln of the initial concentration minus kt. Because you're going to have an x to the negative 1, so the integral of a 1 over x is going to have a logarithm in there, or a natural exponent. Okay? When n is equal to 2, I'm going to get 1 over the concentration at time t equals 1 over the initial concentration plus kt. So So these three are what we call the integrated rate laws, because they have been solved for or developed through integration down here. Okay, again, if you're not in Calc 2 yet, I'm sorry that this is a little bit ahead. We're not actually doing the calculus. I mean, this is how the calculus would get set up, but this is just the result of it. Okay, but if you're there, I think it's making it. I'm hoping it was a good connection for you, Morgan, that you had. All right, it's not a oh my gosh, a scary connection. It's a great connection to see how one thing helps the other. Okay, now what we often do, because we understand that we're looking for this equation that relates concentration to time, we often don't write this little subscript t here, and it's just implied that this is the concentration at the time t that we're interested in. Okay? Other questions? There were other folks kind of whispering or anything? If you have a question, it might be a question that somebody else has later on, and they wouldn't get a chance to actually ask me, so ask it if you have it. No? Okay. At this point, you just need them. Okay? You don't have to derive them any further. They're on your equation sheets. Okay? We just need them, and we're going to start to use them and see how we use them in chemistry. All right? Now, on the one hand, they're pretty simple to use. Let's just go through a couple of quick examples. Yes?
Are there higher order formulas of that, or is it?
Yes. Every order would have its own unique integrated rate law. So higher orders, you would start to see 1 over x squared. You know, it's just going to become a pattern, actually. If you look at the power of the concentration, it was first power, then the ln, then it's the -1. I think it becomes -2, -3. This just comes out of the integrals that we would have for the higher orders. Okay? So, all right. Let me set up a couple of examples for how we might use these integrated rate laws. Okay. I'm just going to use a generic reaction. Let's say x to y plus z is a second order reaction with k equal to 0.025 molar per second. Okay. If you begin the reaction with 1.2 molar x, how much remains after 1.0 minutes? I think I need to change my rate constant. I'm going to add another 0. 0.0025. Okay? This is a pretty logical question, right? You're going to start a reaction with a certain amount. How much are you going to have left 1 minute later, 2 minutes later, an hour later? All right? Sort of the flip of this question would be, how long is it going to take to use up all of the reactants, right? When's the reaction going to be done? When do I get to leave lab, in other words? Right? These are the types of questions that these integrated rate laws can answer for us that our earlier versions could not. All right? They could not tell us these connections between how much stuff we have and how much time has passed during the reaction. Okay? All right, so what's key to this is that it's a second order reaction and we're given the K. For a second order reaction, we can write that 1 over x equals 1 over x0 plus kt. And we're after the x. So we got 1 over the initial amount of 1.2 molar plus 0.0025. This is, I gave the wrong units. I keep doing that. 1 over molar and seconds. And then the time is 1 minute. So I do have to convert that to 60 seconds so that the units cancel out. That's a sneaky little thing that often pops up in our kinetics questions because the rate constants will have per seconds, but you might have a time that's, more like minutes or hours. So you have to justify, those two. Okay? All right, so my calculator, 1.2 raised to the negative 1, or 1 over that power, plus 0.0025 times 60. 0.9833. But that's not my answer. That's 1 over my answer, actually. And it's got units of 1 over molarity, which prove that. So I have to, raise it to the negative 1 power, or flip both sides. And I get 1.02 molar as the amount that is left. Okay? Now you get some idea of what your answer should be when you're doing kinetics problems, because the reactant concentration never increases. It always goes down. So if you're asked a question like this, it's always going to be less than what you started with and greater than what? What's the minimum amount it could ever be? 0, right? So you got to get a number between 0 and your starting value when you're asked about a concentration. If we flip this around and do a time problem, we'll do that in a second. You've got to get a time that's positive. You can't get negative time, right? All right. So you start to think about what are the reasonable windows for an answer, right? And it helps you have some confidence in your answer. Okay. So let's do a different question. How long will this reaction take to use up 70% of the initial amount of X? Okay. How long is it going to take to use 70% of the amount of X you start with? Now the key to solving this problem is to thinking very, very carefully and to understanding the rules of kinetics. The integrated rate laws, okay? So the integrated rate laws, the IRLs, are always written in terms of how much reactant remains at time t. The question could be asked anyway. Here the question is asked about how much is amount being used. But we have to think and answer the question through how much remains at times t. The question could also ask about the products of this reaction. It doesn't matter. We always have to think in terms of reactants remaining at time t. That's what these equations tell us. And so sometimes it adds on these little extra bits and pieces, some stoichiometry or some converting this percentage used to percentage left, like we're going to have to do right now. Okay? So for this problem, when 70% is used, that means that 30% of the initial amount of X remains. Or in other words, X equals 0.3 of what it initially was. Right? So the value of X is 0.3 times the 1.2, or 0.36. So I'm going to use the exact same rate law that I had before, but now I'm not solving for the X over here. I know it. I'm solving for the time. So 1 over the 0.36, because that's how much I have, equals 1 over the 1.2 plus 0.0025 times the t. So I could take 0.36 to the negative 1 power minus 1.2, 1 over that. So far I've got 1.944 equals my 0.0025 times t. So I just divide by the rate constant, and I get 778 seconds. Maybe that's big enough that we can convert it to minutes, right? It's going to be about 12, 13 minutes or so, it looks like. But just keep in mind that you'll be doing these in mastering chemistry. You just pay attention to what unit it puts in the box, and that tells you how you should be answering. Okay? Any questions on that problem? All right, let me do another one to show you sort of a different way we could put together a bunch of these pieces, different order. How about A to produce 2B? If this reaction has K equals 5.7 times 10 to the minus 4, 1 over seconds, how long will it take to produce 0.20 molar B from an initial concentration of A that was 0.30 molar. So this problem is really going to tie together a bunch of things. Because the question's asking us about B, our product. So one connection I see that has to be made is how does B relate to A? Because I have to solve the kinetics from A. As I just had up here earlier in the blue, right? The rate law is always written in terms of the reactant, A, in this problem. All right? And so we're going to have to figure that out. But we're really after a time here. So we got to do some translations. That's what this problem really is at the start. Before we can do the kinetics, we got to do some translations here. In other words, to make 0.2 molar B, how would we get this, right? To make this much B? Well, let's use our stoichiometry. 2 molar B is made for every 1 molar of A that's used. Now I know that's a little different. We're used to using the coefficients as moles, but molarity is moles per volume. So they should track directly as long as everything is in the same container. All right? If they're in different volumes, then we're kind of out of luck here. And you have to do an additional step. You have to convert molarity back to moles using the volumes. Then you do this part here. All right? But for now, there's no reason to believe they're not. So what this means is, I did it upside down, by the way. I want to cancel the B, so it's 2 molar B in the denominator, 1 molar A in the numerator. So to make 0.2 molar A, I need to use 0.1 molar A. I think I said that wrong. To make 0.2 molar B, I need to have used up 0.1 molar A. But that's not A at this time that we're interested in. Although, actually, no, it's not, okay? So if we have used, next step here, if we have used 0.10 molar A, then our initial amount, 0.3, minus the amount we've used, is going to be the amount that's left. So if we've used 0.1 molar A, then 0.2 molar A is left at this time. Now we're ready to solve. Okay? All 3 of your kinetics equations that I wrote, integrated rate laws, have 4 connected pieces. Concentration at time t, initial concentration, rate constant, and time. To solve for 1, you need the other 3. Right? I was given a rate constant here. I know I'm trying to solve for the time. I was given the initial concentration. So these first 2 bits of work were to find the concentration of the chemical at that time. We don't know what that time is yet. Now I wrote ln. That's implying this is a first order reaction. How did I get that? The units. The units. The units up here told me. Okay? I didn't have to spoon feed it to you and say this is a first order reaction. Again, the units, 1/seconds, belong only to a first order reaction. Okay, you can only have those units when your reaction's first order. So it's like staring you right in the face to pay attention to these things. All right. So now I'm after time again. I want to solve for time. So now we can plug in some numbers. ln of 0.2 equals ln of 0.3 minus 5.7 times 10 to the minus 4 times t. So that's going to be negative 0.4, oops, negative sign on that, negative 0.405 equals the 5.4 times 10 to the minus 4, so now divide by that. And I get 751 seconds.
5.7.
Should be 5.7, typo, and that's going to change this, sorry. So a little bit less, 711 seconds. Yep, I should read what my numbers are, I guess, before I write them in there. Okay. So this one's a little more involved. All right. Any questions on it? And so we could solve a bunch of different types of questions now. Anything that connects time and amount can be solved with these integrated rate laws. What we need to know is the order, so we choose the right equation governing the relationship, okay? And then we need to know 3 of the 4 pieces that are in this puzzle in each of the cases. Right? Now there's a lot of other stuff going on with these integrated rate laws. All right. First, the idea of K. K is a little bit abstract. This idea of a rate constant. There's this general, and it is true that as K gets bigger, the rate of the reaction gets faster. So if you're looking at 2 different rate constants, the higher rate constant would tend to mean a faster reaction. But it's kind of abstract, what is a truly big or truly small. So it's we have this way to translate it into something we might understand a little bit better, and that's called the half-life of a reaction. You've probably heard that term before. So the half-life of a reaction is the time required to consume or use up 1/2 of the initial concentration of reactants. And so then if I told you that a reaction had a rate constant of 0.000726, 1/molar seconds, you might be like, okay. But then I said, the half-life of that reaction is 13 minutes. Oh, 13 minutes to use up half of the stuff. All right, that's not too long. Could probably do that in lab, right? It's not going to be too bad of a reaction. Versus hearing that a reaction has a half-life of like 7 days, or 1.6 billion years, as is the case for some nuclear decay processes, right? We understand time because it's what we live in the world of time. And so this is a very useful translation of the rate constant. But so that's really what it is. Half-life is nothing other than a translation of K. to give us a hint as to how long it is. So how the half-life relates to K depends on the order of the reaction. Just like the integrated rate laws did. Okay? For a zero-order reaction, the half-life is going to be the initial concentration divided by 2K. What you see here is that as you add more stuff, the half-life gets longer. All right? Okay. Makes a lot of sense for a zero-order reaction. For a first-order reaction, the half-life is the ln of 2 divided by K. No dependence on concentration. What's interesting with the first-order reaction is that as you add more stuff, the reaction goes faster. Therefore, the amount of time to complete the reaction really stays the same in essence. Okay. In one of the classes this morning, I mentioned a spending spree, right? So if I double your money, I send you on a spending spree one day, then I double your money the next day, you spend faster, twice as fast, so you're going to burn through your money in essentially the same amount of time. Okay, if you're a first-order spender. If you're a zero-order spender, when I double your money, you don't spend any faster. You get to spend it for a longer period of time, though. Right? It's going to last you longer. All right. All right. If you're a second-order spender, though, okay. Uh-oh, look out. As I increase your amount, you actually spend even faster, 4 times faster, okay, if I double your amount. And your half-life actually gets shorter, okay. Now, that's just to use up the first half. And then you kind of reset, and it slows down dramatically. So it's not like it takes you less time to spend twice the amount of money. In the end, it will take you more. But that first half-life is going to be shorter, okay. All right. So these are 3 half-life equations. These are also on your formula sheet. All right. And what these are really doing is giving you the rate constant in disguise. All right. So we've got these 3 different equations here. And what these really do is their real job is to relate the half-life to the rate constant. The subtext here is that when given the half-life, you can find K for the reaction, which you'll then use in the integrated rate law. Okay, so you have to use the K in the integrated rate law like we were doing earlier, but if you're given the half-life, it's just sort of like a detour to getting started. Just like being told the amount that was used versus the amount that's being left, or being asked about the product versus the reactant. So there's just different little twists, and this is another one that gets thrown into there. A hint for you, since I'm feeling generous today, in mastering chemistry, you have a question about nuclear decay. If you are a reader of the textbook and skim through it, you'd find this. But nuclear decay is always a first-order process. It doesn't tell you that when it asks you to solve a problem with nuclear decay, so you need to know the order, but it's first order because those processes are first order. That's another sort of drawback of these half-lives. If I tell you something's half-life is 2 hours, I now am hiding what the order of the reaction is. Versus earlier when I told you the rate constant and the units that connect directly to the order, for half-life, the units are always time, regardless of what the order is. So it kind of is a hiding, a way of hiding what that order is. All right? All right, so that's just another little layer. I'm not going to do any problems with them. They're pretty simple. By the way, these equations are solved for very easily using the integrated rate laws. You would just substitute that x is 1/2 of x0 and solve for t. And you would get these in the 3 different equations, these 3 different relationships that we solve here. So it's not like I invented something crazy or whatever. It's just algebra. Yeah. Okay. All right. right, now the last big piece of this kinetics puzzle that we want to get to today is really the stage setter for our next lab that we're going to do on Wednesday. All right. If I look at these three orders of reactions again, n equals 0. See if I can fit this all into one board. N equals 1 and n equals 2. X equals x0 minus kt. ln of x equals ln of x0 minus kt. 1 over x equals 1 over x0 plus kt. Not sure if you can see it or not, but all of these fit the form y equals mx plus b. They're all written in the same pattern. They're all linearized, in other words. Okay? And this becomes the third way that we can study and determine the order of a chemical reaction by an experiment. Okay? So if you follow a reaction and follow the concentration of your reactants at a bunch of different times, okay, and make a graph of concentration on the y-axis versus time on the x-axis, can you see that your x variable is time, your y variable is your concentration, b is the initial amount? There's a connection between the slope of the graph and the rate constant. Okay? This line, generically, because all lines are y equals mx plus b, but this particular line is x equals negative kt plus x0. But this relationship, here's the unique part. If and only if, an important qualifier, it makes it a two-way street, okay? If and only if a reaction is zero order, will a graph of concentration versus time be linear. And thus, the slope is equal to the negative of the rate constant, or the rate constant is equal to the negative of the slope. Over here in the first order case, it would be a graph of ln of x versus time. That would be linear. Okay? And we could match up these parts. So if and only if a reaction is first order, will a graph of ln of concentration versus time be linear? And when that graph is linear, and then thus, again, k will equal the negative of the slope when I equate the two forms. The generic, every line matches y equals mx plus b to my specific case of ln of x versus t. Lastly, for a second order reaction, 1 over concentration would be plotted versus time. This one would go upwards. And we would write here, if and only if a reaction is second order, will a graph of 1 over concentration versus time be linear, and thus k equals m when you relate the two forms, generic line to the specific variables in play here. Now, how does this help us? Sort of related to the question that we had earlier from James. A reaction's order cannot change, and it can be only one value. Therefore, a reaction can match only one of these three potential possibilities. Now, there are third order and fourth order, but we're limiting ourselves to 0, 1, and 2. So if we don't know what a reaction's order is, a new way that we can find the order and the rate constant is to collect concentration versus time data. We know how much we start with. Then we measure the concentration a minute later, or 10 minutes later, 20 minutes later, 30 minutes later, however often we want to. And we make a graph. If the graph, the straightforward graph of concentration versus time is a straight line, we know the reaction is 0 order. And we just take the slope right off of it when the graphing program adds the slope for us. Okay? The slope is just negative of the rate constant. Bam, we're done. We've got the k in the end. Then we can solve whatever other problems we want with that one. But if that graph is not a straight line, it also rules out 0 order as a possibility because of the and only if part. So what do? We take the ln, natural log of our concentration values, and we make a second graph of those values versus time. Now, if this one comes out to be a straight line, it's because our reaction is first order. Bang, we got the order. The slope tells us the rate constant again. If that still isn't a straight line, we go back to the concentrations and we take 1 over them. Plot those versus time, and hopefully it comes out to be. If none of these come out, then it's not 0, 1, or 2. It's a higher order reaction. But your cases will always be 0, 1, or 2 for this method here. Okay? And we get the rate constant here. So only one of these three patterns can exist. So here's where the handout comes in that I've distributed.